All right, we've got a couple of videos on multiple regression. Don't let the brevity of these videos fool you into thinking that this is not an important procedure. The reason why this is brief is that we're not covering calculations. I generally don't cover multiple regression calculations in this course. They do appear in the tutorial, so you can get some background on that. But that's the reason why this is short. Multiple regression is actually among the most important statistical procedures that we could possibly cover. It's really a workhorse within the field of psychology. All of the variations of it can and do fill an entire course. So we'll start with multiple regression. What is multiple regression? Well, multiple regression means that we're doing regression analyses where we're expanding on simple regression. Simple regression is always with one predictor. With multiple regression, we have multiple predictors. We still only have one outcome variable. It's a different kind of analysis if we got multiple outcome variables. But we can have 2 to 50 to 1,000 predictors. The only limitation is our sample size. We can't have more predictors than people in our study. Each of the predictor variables will get its own slope value. So each value will have a contribution. This contribution could be thought of as its unique contribution, what it contributes that none of the other variables can tell us. There remains only one y-intercept and only one r-square value. So those things remain the same. We'll also bring in a new value that wouldn't have made much sense to talk about with simple linear regression, but is very useful with multiple regression, and that's called the standardized regression coefficient. That's going to be a regression coefficient that's put on a scale that is more like a correlation in that it's bounded from -1 to +1, and it has some of those nice traits that standardization brings. All right, so 2 or more predictors at the same time. We're going to compare this to a model with one predictor. And what we're going to look at are some data that Danielle and I collected over the summer. We were interested in predicting people's support for the Black Lives Matter movement. First, we're going to look at predicting it from just positive contact experiences with African Americans. Very common in my research and also in research within the field of social psychology is to look at how contact with members of certain groups influences your attitudes. And we generally know that if you have favorable contact experiences like friendships with people from other ethnic groups, you tend to have better attitudes toward those groups. We wanted to see if this extended to support for BLM. When we move to multiple regression, we're going to have not just positive contact, but negative contact experiences, realistic feelings of threat, that is feelings of economic threat from African Americans, symbolic feelings of threat. These are maybe threats to your values, believing that certain ethnic groups have different values than your group. So simple regression. Here I'm just predicting BLM from positive contact, support for BLM. One thing we can see is we've got a slope of 6.08. What does that mean? Well, for every 1 point on the 10-point positive contact scale that we rise, we go up about 6 points on the 100-point support for BLM scale. We see a multiple r-squared of 0.1276, or about 13%, suggesting that these positive contact experiences actually predict 13% of the support for Black Lives Matter. Now, this is an analysis we've seen before with the simple, but what we can do in adding multiple regression, and here's the sort of graph that we might see. Well, one thing I wanted to mention about this graph, we have a simple scatter plot here. The 2 things that I've done here, first, I've added a line, and the way you do that is using this AB line command. Now, one thing that's a little tricky about this is the order of things. The AB line command, you're actually giving it your regression equation. So I'm telling it, here's the prediction equation, BLM predicted from positive contact. And that adds in the line. What I did here to make the graph a little bit more readable, you see how when you've got stuff across a pretty coarse scale, and by coarse I mean not that many data points, it kind of bunches up. I've used a function called jitter to add a little bit of random noise there. It moves the points around so that you can better visualize what's happening. I think you can better see the pattern of results here, where the density of the scores is compared to this, which is really hard to read. So a couple new little bonuses in here. All right, multiple regression. Looking at the code above, all we do is add plus the different names of the variables. One thing I've done a little bit differently in this code, you see where it says, I've just got the variable names and it says data equals BLM. You can construct your regression analyses like this as well. But all running multiple regression requires is just simply adding in more variables. It's not any more complex than that. Now, one thing that we'll see is we have our one y-intercept still, 4 different slopes, and still just one r² value. Notice that r² value with the addition of these 3 new variables went up to about 0.19 from about 0.13. So when we add variables, we add explanatory power. We can see a couple of things here. First, positive contact and negative contact both have positive slopes, although negative contact is very small. Similarly, realistic threat has a positive slope, but that's relatively small. Symbolic threat has a negative slope, which means the more you feel like African-American people hold different values than your own group, and this was a group of white people who answered these questions, or self-identified white people, the less support you show for BLM. And that really is multiple regression in a nutshell. All we're doing is adding to what we already have done, adding additional predictors. We get multiple slopes, and that's the big difference. Now, one additional piece to talk about here, these slopes, they more generally get talked about as regression coefficients. That's their kind of formal name. There's a different kind of regression coefficient, which is called a standardized regression coefficient. And those can be helpful here. The reason why these can be helpful is all of these variables are on different scales. Positive contact, negative contact, the threats. I think the threat scales go from like, instead of 0 to 10, they go from maybe 1 to 7 or something like that. So everything's on a different scale. So that 1 point change doesn't really tell us anything. We don't know if 5.65 is a bigger slope than 3.69 because these are all on their own scales. We can standardize these, and the way that we standardize them is by simply requesting a statistic called the standardized regression coefficient. Some people call this the beta, but I prefer standardized regression coefficient. We'll come to that in a second, but I just have a little more information here. I just wanted to show you the regression equation and how that works out. We're just simply adding stuff on to the end. All right, standardized regression coefficient. To get that, we need a package called quantpsych. There's other ways to do it, but it's easiest to the quantpsych package. And the command is lm beta, and we issue that on the object that we made, where we saved our analysis. And the lm beta command will take that and it'll spit out these standardized coefficients. One thing to note here, positive contact is a little bit bigger than symbolic, but they're really about on the same scale, whereas realistic is very small, negative contact is really small. In terms of interpreting these are interpreted in terms of standard deviation. So a 1 standard deviation change in positive contact relates to a 0.33 standard deviation change in support for BLM.